Well, here's stoichiometry test review, the last three questions, questions 13 through 15. And in this one here, we've got 1 mole of nitrogen gas reacting with 3 moles of hydrogen gas, producing 2 moles of ammonia, NH3. So this one we had to modify a little bit because in the question we had you cross off this first part. So this is our given, 14 grams of nitrogen. And we're looking for how many grams of hydrogen. So sorry for the little bit of confusion. We had a problem there from another time. So to get working on this one, let me get a piece of fresh paper here. We're ready to go. Let's cover up that stuff so we don't get all confused. So with this question, we're going from grams of nitrogen to grams of hydrogen. Using our roadmap, we're going to be going from grams. In fact, let me set this side up as grams nitrogen because that's what our given is. So I always like to set up the givens on this side. And we're going to grams of hydrogen. So let me erase this from a previous one. So we're looking for H2. Now remember, it's H2 is hydrogen gas and it's N2. That's important when we're doing gram-gram problems because you don't want to accidentally think that it's just one atom of nitrogen in nitrogen gas. So we're going from here, convert to moles, do our mole ratio of moles of hydrogen over moles of nitrogen. Then once we get to moles, we're going to convert back to grams. So let's get this set up. We always start with what's given. In the problem, we are given 14 grams of nitrogen. Oh, look at me. Let me replace my pen with a pencil because I'm pretty confident here, but whenever you do stoichiometric problems, use a pencil. It'll make life easier. So now what we need to do, we've got the given here, which in our problem was 14 grams of nitrogen. Is that correct? Yeah, make sure I'm right. So we're given 14 grams of N2, and we need to convert that to moles by setting up the equation of moles per the molar mass for nitrogen. So moles over grams. 1 mole of N2 is, and we're going to look on our periodic table, nitrogen by itself would be 14, but since we have 2 nitrogens, N2, it's going to be twice 14 or 28 grams per mole. So let's see, 28 grams of N2 in 1 mole of N2. We can now cancel out that, and we've successfully converted to mole. On our roadmap, we need to set up our molar ratios. Mole B over mole A, and mole B is moles of H2 over moles of N2. So moles of H2, in this balanced equation, we have 3 moles of H2. 3 moles of H2. And we're coming from nitrogen, we have 1 mole of N2. So at this point now, we have successfully converted from nitrogen into moles of H2, and now we just need to convert it back to mass because that's the problem's looking for. Scoot it down. There we go. Convert it into mass. And when we go from moles to mass, the conversion factor is it's grams, the molar mass, grams over 1 mole. So let's see. We've got in 1 mole of H2. Now H2, you should probably know that by now, but mass of 1 hydrogen is 1, and since we have 2 of them, it's 2 grams in 1 mole. 2 grams of H2 in 1 mole of H2. Those cancel out right now. And now, let's cross-cancel where we can to make this easier. And let's see. Now we've got 28 and 14. Those easily cancel each other out. So we'll cancel out 14 to 1 and 28 to 2. And then as we look at the problem here, we have 2 grams of H2 over here, and we have a 2 here. So we can cancel out the 2 here. That makes this just 1. And we'll cancel that out. That makes this now just 1. So in our problem, we're going to end up with 1 times 1 times 3 times 1, which is 3, divided by 1 times 1 times 1. So it's 3 grams of H2 in this problem. Now we're going to work on question 14. Question 14, I told everybody that a dm cubed, that's decimeter, cubic decimeter, that's the same as a liter. So I had you just fix that. We didn't want to trick you out on here. And in this problem now, we've got iron oxide, basically rust, reacting with carbon monoxide to make 3 carbon dioxides and 2 iron atoms over here. So let's see what the question's given us. How many liters of CO? So that's what we're looking for. Liters of, of CO. And it's not CO2, it's just CO. When there's an excess of Fe2O3, okay, that's kind of extra information that we don't really need to know, to produce 5 moles of Fe. So we have 5 moles of iron. So that's a given, 5 moles of Fe. So we're going to be working between iron to carbon monoxide. So I want to get my equation triangle set up for this problem. So the given in this problem was 5 moles of Fe. So I tend to like to make my givens over here. This will be Fe. Let me get rid of this from the old problem. And we're looking for liters of CO, of carbon monoxide. So let me get this side set up. This is our carbon monoxide, CO. And we're looking for, I already got it set up from a previous problem, looking for liters of CO. So we're starting down here with, we're starting with 5 moles of Fe. So we're starting right here at moles. We'll have a mole-mole conversion, and then we'll end up with moles of carbon monoxide, and then we're going to use the conversion into volume, multiplying by 22.4 to get us back to liters of CO. So there's our roadmap. Molar conversion, and then mole to volume conversion. So let's get that set up. And that was what we were, there's the paper where what we were given. So I'll rewrite this here. 5 moles of Fe, that's iron. And right away we're doing the mole-mole conversion. So we need to see how many moles of carbon monoxide there are in this problem. And we have 3 moles of carbon monoxide, 3 moles of CO, and how many moles of iron do we have in the balanced equation? 2 moles of iron, we go by the coefficients, 2 moles of Fe. So now we've converted now in this step from moles of Fe, we've now converted to moles of carbon monoxide. So in our problem, we are now right over here. We've gone from the mole to the mole of carbon monoxide. Now we just need to multiply, because whenever we go away from the mole, we're multiplying. In this case, we're multiplying by 22.4 liters per mole. So we say 1 mole of carbon monoxide is 22.4 liters of carbon monoxide. This will cancel, and this will cancel. And let's see, I'll use my my green pen today. Now on this one, let's see. Well, I'm just going to cancel. Looks like this one here. 2 goes into itself 1 time. 2 goes into 22.4. Well, it's half of 22.4, so that'll be 11.2. So our answer on this one, well, let's see. So we got 5 times 3. This equals 5 times 3 times 11.2 divided by 1 times 1. Now in this particular problem, this is of all the problems we practice, this is one of the few that it just doesn't break down any easier. So I'm going to do, this will be the same as 5 times 3 is 15 times 11.2. So, well, we just got to set that up. 15 times 11.2. And when you do the math, when you work it out, you know, when you get it all multiplied out, you're going to end up having, let's see, it comes out to 168 liters, because we're looking for liters of CO. So it wasn't a easy or quick conversion to go to, but we end up with that number there. 168 liters of carbon monoxide. And then the last one, Question number 15. It asks, what is the importance of the coefficients in a balanced chemical equation? Well, first off, here's a balanced chemical equation. The coefficients multiply the numbers of all these atoms so that we end up with the same number of atoms on each in the reactant side as we have this in the product side. So for example, we've got 3 times 1 carbons, 3 times 1 carbons. That was our last unit. So first off, coefficients are the way that we balance the equations, get the same number of atoms over here and over here. And that's part of the law of conservation of matter, is that we've got to have the same number of atoms over here as we do over here. So first off, the importance of coefficients, it balances the equation. Reactant atoms equal product atoms. And then the second thing why this is important for us, when we're doing the conversions in this last problem, we had to convert from moles of iron into moles of CO to carbon monoxide. These tell us the ratios, the proportions. There's for every 2 atoms of iron, for every 3 molecules of carbon monoxide in that last problem, we had 2 of these. So they help us set up our molar ratios. Molar ratios are based on the coefficient. So, there we go. That ends the review for the stoichiometry test. Biggest thing right now is you make sure that you can set this conversion table up, because if you can do that, you're going to have your roadmap. It's going to help you figure out how to do these problems. All right, that's it. Cut.